Okay, so let's continue. Last time we calculated the U effective, which is the effective Coulomb interactions of an external perturbed Coulomb potential due to the test charge Q, and there's also the background Coulomb energy contributed from all other electrons. So we have U and V, and we collected only the contributions to U, which has this following term, where the first term is just unperturbed, the bare Coulomb potential U, and the second term is the second order contributions to U contributed from V times U, or U times V, and they are the same, so we get a factor of 2, and this is the resulting contributions. And remember, this is just a so-called one loop correction, which is up to only second order in perturbation theory. Okay, so diagrammatically, we simply just use this bubble, a single bubble, representing such a correction to the U, which is something inside the red bubble, is the correction to the bare interaction vertex for the Coulomb potential U. However, we could imagine that this contribution can go on from the higher order in perturbation, perturb the expansions, and so I use dot 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 represent the additional contribution from higher order terms, and such higher order terms under so-called random phase approximation is exactly this form of the bubble diagram, like this. And we postpone this calculation of the single bubble, and we could actually imagine that we already know the answer to the one loop corrections, and we could sum up all diagrams like this, called the ring diagrams, and imagine we consider U effective from the contributions of the ring diagram like this. So in general, we can have as many loops as possible, starting from one loop, and the total contributions to U effective is the bare one plus the single bubble and two bubbles and three loops. So remember, the interaction that links neighboring rings or neighboring loops are the V interaction, and V interaction is the Coulomb interaction of all different electrons other than the charge lead to this U potential U, and the potential U is actually put at the very end of this ring diagram. In other words, we only need to sum over all such ring diagrams from 0 ring and 1 ring and 2 ring and 3 ring up to infinite number of rings. And such a diagrammatic summation is called the RPA. So as I mentioned, the random phase comes because of the Fourier phase or Fourier coefficient, which represents arbitrary phase. Okay, so each ring diagram represents a specific order in perturbative expansions. Okay, so we need to sum over all such ring diagrams to get the total contributions, and so let's just look at this summation. Mathematically, you could simply just sum over all such a diagram. If I made, this is simply just a simple single bubble plus VQ squared, two bubbles times U. Okay, so you can simply just plug in what we had for the single loop corrections, and this loop will be repeatedly appearing in front of this u, and then we simply just square them for this two-loop correction and cubic them for the third, say the three-loop, and so on and so forth. And you can see very clearly that this is nothing but a geometric series, right? And suppose I simply just consider this single bubble as x, and the two-loop correction gives you x squared. Okay, so if I simply just extract all this common factor u, and this becomes the following: 1 plus x squared, right? Okay, where x is just this complicated object inside the orange bubble. Okay, and such geometric series is easy to solve because you know that from high school, right? Okay, this is the infinite geometric summation, and the answer is what? Is u divided by 1 minus x, right? And so we define this as u divided by this dielectric function epsilon. And epsilon of q is called static dielectric function, which is the same dielectric function that you already learned from the introductory solid-state physics. So now we apply quantum mechanics and many-body physics to really derive such static dielectric function. Static refers to the fact that this is just a static charge distributions, and we have not discussed the dynamical dielectric function, where this epsilon is also a function of omega, where omega is the frequency of your AC field, external AC field, and you could also apply the external AC field with the frequency omega and to probe this dielectric function. Okay, so this is not a constant anymore. This is a function. Okay, so in electrostatic EMN, we know this dielectric constant, but here it's not just a single constant, but it's a series of constants, and that constant depends on q, where q is your momentum transfer of electromagnetic waves, or the Coulomb interaction. In other words, the Coulomb interaction leads to the momentum transfer q, and different q will lead to different static dielectric constant. So if you collect all this dielectric constant, as a function of a q, and you get a dielectric function. So this is a dielectric function of q. So what is epsilon? And this epsilon is given by this one bubble. So this is a very important result, that if we sum over all these ring diagrams, and we get dielectric function which modify the bare Coulomb interaction u. So the effective u now becomes the bare u divided by this epsilon q. So you see, this is the modification of your Coulomb interaction, right? So the bare one is not what you see in this many-body environment. Instead, it is the u effective that all the electron or charges will see. Okay? And that effective corrections come from the presence of other charged particles. Okay, so that's the meaning of this correction, because inside this bubble, you connect all the rings by what? V of q, right? So the V is, as I mentioned many times, is the Coulomb interactions of different electrons, okay, other than this U potential will give. So in other words, the presence of the other electrons will modify the Coulomb potential in this form. So the remaining job is to calculate this epsilon q. Namely, we should explicitly calculate the summation over P, this complicated object in the numerator and denominator, and really simplify this one loop correction. And we plug in this one loop correction, and we immediately see the Yukawa potential, or the screened Coulomb potential, and we could reconnect this Thomas Fermi result that we derived by a semi-classical result, approach. But this is the more standard and completely quantum mechanical treatment. Okay, it is the most reliable result, which is the RPA. Very good. So now we erase the blackboard, and when we come back, we will explicitly derive the this epsilon q. So we should calculate this epsilon q. Okay, so let's try to calculate this so-called one loop bubble, which I define this as chi of 0 as function of q. This epsilon of q is what 1 minus v of q and chi 0 of q. So there's a 0 here in the subscript, implies that this is a static dielectric function, and which means that this omega, this AC frequency, is 0. And we are also interested in this long wavelength fluctuations, or the short q limits. Okay, the small q limits, meaning we get very small momentum transfer, and we get very long wavelength fluctuations. Okay, so in a small q limit, q goes 0, we could do Taylor expansion for this numerator, which is the difference between the Fermi function at different momentum. One is p plus q, another is p, but this q is very, very small. So that we could Taylor expand this difference in Fermi function, and we sum over spin, so we got a factor of 2, and we could convert the summation over p into momentum integral over a three-dimensional momentum space. Okay, so when we do Taylor expansion, we forget about and neglect all the other higher order Taylor expansion terms, so we only keep the linear, this leading term, which is the linear order in this energy difference, and therefore you immediately see that you get a cancellation between the numerator and the denominator, which contains the same energy difference. Okay, so you end up summing over or integrating over this the derivative of this Fermi function with respect to the energy. As I mentioned, the Fermi function at 0 temperature limit is a step function, right? So the Fermi function is a step function, which is 1 below the Fermi energy and 0 above the Fermi energy. So then if you take the derivative of this and f with respect to the energy, you'll get a sharp dip or a peak, which is the Dirac delta function. Okay, so because if you take the derivative, and this will be a minus delta function, epsilon minus epsilon f, because this is a jump downwards, right? It's a downward jump from 1 to 0. If you take the derivative of this Fermi function epsilon right at Fermi energy, you get a negative infinity of a delta like dip, and therefore you could estimate this as what is minus what the epsilon p and mu plus epsilon p minus dn d epsilon p, where mu is the chemical potential or Fermi energy. So then you end up getting this density of states at the Fermi energy with a minus sign, because this is the plus sign because there's a minus sign here. So this is the Dirac delta function, and you integrate over this entire energy range with this Dirac delta function, you get the density of states right at the Fermi energy with a minus sign. So now we could plug in such a density of states back to this epsilon of q, and we will try to evaluate this. So it's U effective, which is what? U of Q divided by epsilon of Q. And this is what? Minus 4 pi ZE square divided by Q square. This is the unscreened Coulomb potential, U of Q, and epsilon of Q, so 1 minus 4 pi E square over Q square. This is V of Q times chi of 0, and chi of 0 is what? Minus density of states at Fermi energy. Okay, so you plug in the results and you get what? Minus 4 pi E square divided by what? You multiply this Q square on both sides, okay? The numerator and the denominator, you multiply Q square on both, and you get this minus 4 pi ZE square. In the numerator and the denominator, you get Q square plus 4 pi E square times the density of states at Fermi energy. Okay, so here comes the Thomas Fermi result. Okay, so you can very clearly see that this is nothing but what? This K Thomas Fermi square. Yes? Okay, so you would check whether this is really the same as the Thomas Fermi wave number, K Thomas Fermi, that we derived last time by the semi-classical Thomas Fermi approach. Okay, so then we could call this Ks square. So this is Q square plus Ks square. And this Ks is the same as Thomas Fermi wave number. And so Ks square is the same as square of the Thomas Fermi wave number, and which is nothing but 4 pi E square times the density of states of your metals at the Fermi energy. Okay, so now we have a more quantum mechanical results for this Thomas Fermi wave number. Okay, so later we'll check whether this KTF is really this 4 pi E square times density of states. But here we are satisfied with this results, but we could rewrite this KTF or Ks in this standard unit in solid state, which is this Bohr radius A0 and Rydberg constant 13.6 electron volt and so on. So remember, our standard units in solid state is always the Bohr radius and the Rydberg constant, okay, and so on. So let's do it. This Ks is the same as K Thomas Fermi, which is square of this minus 4 pi E square chi of 0 of Q, where Q is 0. So this is 4 pi E square density of states at Fermi energy. And you know very well what this density of states at Fermi level is for a non-interacting Coulomb free electron gas, right? So you know that from your introduction to solid state. So a standard conventional metal for three-dimensional, say, Fermi sphere, you could very easily evaluate this density of states. So let's do it. And you could show that this is given by 4 divided by pi Kf by A0, which is 4.6 divided by Rs. So Rs, remember, is the dimension is radius in units of Bohr radius, A0, right? Electron radius relative to the nuclear core. Okay, so this is your homework. You have 2 sub-homeworks. Number 1 is to derive this equation, and number 2, you estimate this. You could also reduce this, the first line to the second line by plugging all these numbers, okay, in units in terms of Rs. Okay, so Kf is a function of Fermi energy and mass and h bar and so on. The hint to get this are the following, that you could calculate this 1 over this number density, which is the inverse of your number density, the number of particles per unit volume with the inverse, which is simply just the volume of the sphere, which is given by this volume of the Fermi sphere, and so on. Okay, and so you could convert this to the expressions in unit of Rs like this. So you could take advantage of such a unit conversion for free electron. SOMO for a gas, and then plug in this kind of expression, and you get this result. Okay, so let's just estimate this Ks, which is the Thomas Fermi screening wave number. And here comes another homework. Please check whether this is indeed the same as the KTF that we derived some time ago, right? So is it really the same? If you go back to your earlier note that we derived by Thomas Fermi approach the Thomas Fermi wave number, KTF, which is given by 6 pi n e squared divided by epsilon f. So now you could use these identities for a SOMO for electron gas, and can you convert this KTF into Ks, which is from our RPA. Okay, so the right-hand side of the results come from Thomas Fermi semi-classical, and the left-hand side is purely quantum mechanical RPA. Are they really the same or not? You need to check. Okay, so let me just write down some useful estimations of these numbers in what is Ks in ordinary metals. So Ks is about 0.1 divided by nanometer, and one estimation is what 1.8 times 10 to the 8th divided by centimeter. So for example, and your Ls, which is the inverse of this Ks, 0.5 10 to the minus 8 centimeter. Ls is the cutoff. Remember, this serves as a cutoff distance beyond which the two electrons cannot feel any Coulomb interaction anymore, or at least it is exponentially decayed Coulomb potential. Okay, so this is the case for normal metals, but you could check all these numbers in our textbooks for ordinary metals, and these estimations agree with this, the screening lengths and all these dielectric functions that we calculated here. So today we just introduced the standard RPA to estimate this Coulomb screening effect. So now you get this result of the U effective, which is 1 over Q squared plus some square of constant. And that form is precisely what we already mentioned, so-called this Coulomb screened potential or Yukawa potential. Okay, so I believe I assigned this Fourier transformations of the U effective back to the real space some time ago, right? So I don't need to assign this homework for you again. So if you Fourier transform this U effective back to the real space, so this is in momentum space, in the Q space. But if you really plot this U effective in real space by inverse Fourier transform to the real space, then this is nothing but exponential decay of your Coulomb potential, and the cutoff is precisely this Ls. Okay, so if this Coulomb potential is not screened, what you expect is this 1 over R potential. But when you account for the screening effect, this is an exponential decay times 1 over R potential. Okay, and we fully recovered what we expect when this Coulomb potentials due to other charged particles are included in any calculation of any Coulomb potential. So now you could understand this screening effect also occurred for the V. Okay? So up to now, we only estimate the screening of U because of V, right? So, but you could also think about this screening vice versa, or in the opposite way, that the presence of a U also modify the Coulomb potential of V, and these calculations are exactly the same. In other words, the presence of V modify the U and give rise to this U effective. At the same time, the presence of U will correct or modify the V, and so V now becomes V effective. And V effective has the same form as U effective like this. Okay? However, when we calculate this screening effect, we should assume the potential of other charged particles stay unscreened. Okay? And therefore, if you calculate the U effective, this V of Q here should be the bare one without correction, and vice versa. So if you correct this V by U, and this U should be kept as the bare level. Okay? So, but once we understand the screening, the mutual screening effect, and when we consider everything, so both V and U becomes V effective and U effective respectively. Okay? And then we should forget about this RPA. Okay? So this derivation that I show you today is the process or the procedure that we get the Coulomb screened potential. But after we consider the Coulomb potential, so the screening effect, and both U and V becomes U effective and V effective. And from now on, we should only consider the screening Coulomb potential, meaning for all this Coulomb potential, regardless what's the origin of these charged particles, they should behave exactly the same as U effective or V effective. So there should be no such a thing as a bare Coulomb potential anymore, because we know that they should get screened anyway. Okay, so this is the important lesson that we learned today, that in this Coulomb interacting many-body electron state, we have a Coulomb screening, and we could use RPA to sum over all the ring diagrams, and we get effective the Thomas Fermi wave number, and this gives rise to the screening of a Coulomb potential. So now it comes a circle, and we come back to the original point where the Hamiltonian of this Coulomb interacting electron gas should be represented in terms of the density operator. That's for sure, because we can recover everything we know phenomenologically, experimentally, and also semi-classically. Okay, so we say goodbye to Hao-Jun Falk, and we welcome RPA from now. Okay, so this is the happy ending today. So now you get clear and complete picture of why this Coulomb potential is corrected or modified, okay, theoretically and also in principle. So I guess you are able to understand everything I mentioned today by reading our textbooks and doing the homework problems by yourself, because I already provide you with enough information and hints. So on Wednesday, we'll start a new chapter, which is the second quantization for a bosonic operators, okay, such as phonons and harmonic oscillators, and also spin excitations called the magnons. And we will discuss those quasi-particles after we define this creation and destruction operator for a boson. It's in the middle of our semester, so I hope that we could cover up to superconductivity, the PCS theory, by the end of the semester. Okay, so by the end of the semester, you should understand almost everything that you already learned in the introductory level of a solid state, but in a deeper way, in a more fundamental way. so we could end our lecture early today. Bye-bye.